Good morning, good afternoon, and good evening,
Uh,
dear colleagues. It is my great pleasure to open next meeting of the International Monthly Seminar, Timescales Analysis. Today we have two talks. The first talk is Wirtinger-Type Inequalities on Timescales, Rectifying Reformation and Improvement. This talk will be given by Sanket Tikare. Please,
yeah.
welcome.
So shall I start?
Yes.
Yes.
Yeah. Okay. Thank you. Hello everyone. Myself is Sanket Tikare from Ramniranjan Jhunjhunwala College, Mumbai, India. So today I will be talking on vertical type inequality on time scale, certain rectifying reformation and its improvement. So first of all, I would like to thank Svetlin for giving me this opportunity to present our work. Yeah. Yeah. This is my college, Ramniranjan Jhunjhunwala College, which is situated at Ghatkopar in Mumbai, India. If any one of you are planning to visit Mumbai, then do come and visit my college. So here is my office, you can see. And these are my collaborators for this work, Raquel Di Costa, Svetlin Gorgio, Jermin Zen Lobo, Suraj Krishna Parmekar. I would like to thank them for their excellent hard work for this talk as well as this work. They have contributed a lot. Yeah, the outline of talk is as follows. First, we will discuss certain auxiliary inequality. Then we will discuss some existing dynamic vertical inequalities on time scale. Then we'll identify a flaw in the dynamic inequalities, vertical inequalities. Then we discuss reformation of those vertical inequalities, how to reform them. Then we improve those vertical inequality and that are given in this section, that is some improved dynamic vertical inequality on time scale, and finally the concluding remark. Okay, let us start. uh, yeah, this talk is based on these two resources. First one is some vertical type inequality on time scale and their application by Ravi Agarwal and his co-authors. And then this another book, classical and new inequalities in time in analysis. Okay, in this work we have used some known inequalities which are given as the auxiliary inequality in the form of theorem 1, theorem 2, theorem 3, theorem 4, 5, 6, and usual our known dynamic voltage inequality is this one. Okay, existing dynamic vertical inequality. There are various versions of vertical inequalities. So we discussed two types of vertical inequality in this talk. The first one is that given in this theorem number 8, that is, suppose gamma is odd integer which is greater than 1, and m is a positive function whose derivative is either positive or negative. Then we have this, let me go here, we have this equation 1 where uh, uh, y is function, RD continuous function, whose derivative is also RD continuous and satisfying these two conditions, and psi is the largest root of this algebraic equation, equation number 2. So this is one vertical inequality. The second one is this one. Again, we have a gamma to be non-negative odd integer greater than 1, and m is positive function whose derivative is either positive or negative. Then we have this inequality of in the form in equation 3, where y is again the function satisfying these two conditions, and phi is the largest root of this algebraic equation, equation number 4. Okay, before proceeding to the proof of this theorem number 9, we shall first declare some notations. That is, for an odd integer gamma greater than 1 and a positive function n, we have alpha to be defined as the supremum of this quantity, and beta is the supremum of this quantity, and a is integral a to b of this function, and b is integral a to b of this function, where this m and y, they are defined as in theorem 9 here, m and y. Okay, and we set c to be the a to be the number a upon b to the power 1 over gamma plus 1. Okay, so these are the some notations which we declare. Now let us start with the proof. First, we claim that b should be greater equal 1 over pi to the power gamma plus 1 times a. We notice that according to the definition of a is defined in this way. So we can remove this modular sign, but we have to write, or we have to multiply by sine of delta derivative of m at a times integral of this one. Then now performing integration by part formula, we have a equal to sine of delta derivative of m at a times this integral, which we call a. Now, keeping in mind the conditions which are imposed on y, that is y of a equal to 0 and y of b equal to 0, we can write a is equal to this minus sine of delta derivative of m times integral of this. From that, we can write a is less equal integral a to b of this quantity, which is 9. Now, we apply the Poisson chain rule, and we have this one. Now, putting the modulus, we get this equation 10. Now, we apply theorem 2 with u equal to yt and v equal to h mu t, y to the power delta, that is delta derivative of y, in equation 10, that is in this equation, and we obtain this inequality 11. Okay. Now, substituting this in 9, 9 is here, so we replace this derivative with this one in 1, that is given in 11. So we get a is less than or equal to this quantity, which we call that as 12. Okay. Next, we apply Holder's inequality, which is given in our auxiliary inequality section, that is theorem number 7, to this inequality, with f equal to this function, g equal to n to the power sigma delta derivative of m to the power gamma upon m to the power gamma, y mod of y to the power gamma plus 1, p equal to gamma plus 1, q equal to gamma plus 1 over gamma. Then applying Holder's inequality, we get this a is less equal this big expression, that is 2 to the power gamma minus 1 gamma plus 1 alpha times this integral to the power gamma over gamma plus 1 plus 2 to the power gamma minus 1 beta times this integral. Now, resubstituting a and b and rearrangement in terms, we get a upon b to the power 1 over gamma plus 1 is less equal 2 to the power gamma minus 1 times beta inside the bracket beta b over a to the power gamma over gamma plus 1 plus gamma plus 1 alpha. That is, but our c is nothing but that in the form of a and b. So using that, we have this one, c to the power gamma plus 1 is less equal to 2 to the power gamma minus 1 times beta plus gamma plus 1 alpha c to the power gamma, that we call as inequality 13. So according to the definition of c is this one, c is greater than 0 because a and b are positive. Now next we apply theorem 4 with u equal to c and v equal to 1 and L gamma is this function. Then we get this inequality 14, that is c plus 1 to the power gamma plus 1 less equal c to the power gamma plus 1 plus gamma plus 1 c to the power gamma plus 2 to the power gamma minus 1 into gamma plus 1 c to the power gamma, that is inequality 14. So from inequality 13 and 14, we can write inequality 15 like this. Now again, we use theorem 3 with m equal to c in this inequality. M equal to c, we obtain this one, this inequality 16. Thus, we got that, but remember that phi is the root of that equation number 4, which is given here. that is c can be replaced by x. So phi is the root of the largest root of equation number 4. So from this we obtain c is less than or equal to phi, that is inequality 17. So on replacing c in terms of a and b, c is in terms of a and b, that is a over b to the power 1 over gamma plus 1. So we substitute here and we got that a to the power 1 over gamma plus 1 is less equal phi of uh, alpha beta gamma times b to the power 1 over gamma plus 1, and which is nothing but 7. Let me go a little back. What is 7? I will show you. Yeah, this one show 7, and that is nothing but uh, this inequality 3. Uh, yeah. So we got 7, and which is what is our claim, and this completes the proof. Okay. Yeah. Now let us discuss about the flaw in the dynamic inequality. This one, which we discussed just now. So let us take one example. That is, suppose t is the time scale, and it is given as the set of integers, and gamma equal to 3. It is an odd integer greater than 1, and take m as the identity function. Then we observe that the derivative of m is positive, and sigma t is t plus 1. We take the function y as the yt equal to t minus 1 into t plus t minus 5. Then using this data, we obtain alpha equal to 2 to the power 3 upon 4, beta equal to 1, a equal to this one, b equal to this, and c is approximately equal to 0.465. Yeah. Now, substituting the values of alpha and beta in inequality 4, we get this cubic algebraic equation. Yeah. And this has only one real root, and which is given as minus 0.46. Yeah. So we find that from e equation inequality 17, we see that phi should be less than, c should be less than or equal to phi, and phi is this. So from that inequality 17, we got that c should be less than or equal to minus 0.46, but c we have obtained as 0.465. So this contradicts to the fact that c is positive or c is greater than 1. So this is not correct one. Further, we observe that phi to the power minus 4 a times a is greater than b, which again contradicts to inequality 3. So further, if we assume that c is less than 1, so here this contradicts to the fact that c is greater than 0 and c is greater than 1. So let us assume that what will happen if c is less than 1. So if we assume c is less than 1, then inequality 3 is also not preserved. So this can be given in the following example. That is, let us take time scale t to be singleton 0 union 2 to the power n naught, and again m as the identity function, and then sigma t is 2t, and m is RT continuous function whose derivative is 1, it is positive. And from this data, we have alpha equal to 2 to the power of 3 upon 4, beta equal to 1, and substituting alpha and beta and gamma in equation inequality 4, we get that the algebraic equation, this is again a cubic equation whose largest real root is minus 0.488046. Yeah. Now let us take yt equal to t minus 1 times t minus 8. Then we say that this y is function, CRD1 function, and y of 1 and y of 8 both are 0, and its delta derivative is 3t minus 9. Okay. Now using these values of y and m delta, we get a equal to this 85536, and hence the value of the right hand side of the inequality 3 comes out to be, that is, which is nothing but a over 5 to the power 4, which is this big number. On the other hand, the left hand side of 3 turns out to be b, which is 173664. So from this we observe that b is not greater than or equal to a over 5 to the power 4. So hence the inequality 3 is not true. It doesn't hold in this case. So here we observe that, here we remark that the inequality in the proof, the error in the proof of theorem number 9 is because of the choice of u and v to obtain inequality 16. Now, In order to apply theorem 4, we should have C should be greater than 1. And because V is 1 and U is greater than V. So in order to C should be greater than 1, so because this we have taken this one. Next, this observation is made in example number 10 and 11, and that can be explained in this proposition. That is, if we take Pt is this expression where t is greater than 1 and gamma is an odd integer greater than 1, then delta derivative of p is less than 0. And from this proposition, we can say that since delta derivative is less than 0, the p is decreasing function for any t greater than 1 and delta for an odd integer gamma greater than 1. Also, we observe that pt is less than 0 because of this quantity, because of this inequality, that is t plus gamma over p, t to the power 2 is less than t to the power gamma plus 2 to the power gamma minus 1 times alpha plus 1 t to the power gamma plus 2 to the power gamma minus 1 times beta over gamma plus 1. Thus, we see that C for C greater than 1 and odd integer gamma greater than 1, we have this C is greater than phi, that is inequality 18. So we observe that inequality 18 is valid in the context of example 10, and therefore inequality this one, which is given in theorem number 4, theorem number 8, that is C is less than or equal to phi, is incorrect statement. Now on putting the values of C in terms of A and B and rearranging the term, we got this inequality. Hence, substituting the values of A and B, we got this one. So this is not the Wirtinger inequality. Here, instead of less than, we should have greater than or equal to. So this implies that the theorem number 9 is not a correct, it is an incorrect statement. Yeah. Again, we have observed that there are certain time scale for which this theorem number 9 is true. So we have this one. The first example is if we take the time scale as t square with the similar function and yt as t minus 1 into t minus 9. Then from this data, we got the parameters alpha, beta, A, B, and C like this, and C is 0.612. Again, substituting the values of alpha and beta in inequality 4, in equation 4, we got this cubic algebraic equation, and this equation has only one real root, and which is nothing but phi, which is approximately equal to minus 1.28. Yeah. So thus we have C is less than minus 0.128, and we have this one phi to the power minus 4 times A is less equal B, and therefore inequality 3 holds on the considered time scale, that is n square. However, we observe that there exists time scale with suitable choice of functions as illustrated above, that is m and y, for which the condition on theorem 9 hold true, but C is less than 1. This is again given in the next example, that is in the example 11, we get C is less than 1, and therefore theorem 4 cannot be used. Moreover, since alpha and gamma are non-negative, therefore the leading coefficient of equation 4 is always non-negative, is always negative. Sorry. Therefore, keeping in mind the fact that p is decreases, we got that limit pt as t tends to minus infinity is minus infinity, which is 19. Also, phi is the largest root of equation 4. So this equation 19 implies that pt is less than 0 for t greater than phi. If this is not true, then we get a contradiction that pt is greater than phi, which is not true. Now, since c is greater than phi and pt is less than 0 for all t greater than phi, so we have pc is less than 0, it is negative. But according to this calculation, we obtain pc as 19 point this one something, which is strictly greater than 0, which contradicts to the inequality this one. Yeah. Now, reformulation of the inequalities. First, we prove this lemma, that is u and v are real numbers and gamma be an odd natural number, satisfying this condition. Then we have this inequality 20. This lemma we required for proving our uh, improved Wirtinger inequalities. Okay, now reformation of theorem 9. Theorem 9 can be reformed in this way. So here the statement is almost same as theorem number 9. Just we have replaced this algebraic equation, this auxiliary equation, this one. So if we replace that algebraic equation with this one, then there is no need of the condition that is c greater than 1 and all this. So here I will be skipping the proof of this because of shortage of the time. So we directly go to the example. So in example number 10, with this uh, auxiliary equation, in the example 10, if we substitute those values of parameter, then we get this equation number 23, and we obtain that c is 0.465 as usual, as we have obtained in equation in example 10, which is less than 2 to the power gamma plus 1 times alpha. And the root of this equation 23 is given by phi, which is 43.64. So after doing some computation, we obtain that a over phi to the power 4 is strictly less than b, and therefore this inequality for 21 holds. Therefore, this holds. Second example, again in example number 11, we get the same equation as in 23, that is this one, and C is obtained as 0.84, which is strictly less than 2 to the power gamma plus 1 times alpha. And after calculating, we got that A over phi to the power 4 is less than B, and therefore again inequality between holds. Another example, in an example 12, we get that algebraic equation, auxiliary equation, as equation number 24. And here C we obtained as 0.612, which is again strictly less than 2 to the power gamma plus 1 times alpha. And the root of this equation is phi. One of the real root of this equation phi is 47.67. Again, calculating this, we got this a to the power a over phi to the power 4 is less than b, and therefore the inequality 21 holds. Now we state some improved dynamic vertical inequalities. So here I will state only the statement, so I am not going into the detail of the proof. Let a of gamma be a smallest positive constant for which that equation 4 holds, and gamma is a natural number which is greater than or equal to 2 such that it satisfies this condition, and m is positive function whose derivative is either positive or negative, and alpha is less than this quantity, beta is less than this, and phi is the largest positive root of this algebraic equation. Then for any y satisfying this condition, we have this inequality. So this is improved version of the vertical inequality. Note that we are replacing this auxiliary equation. Then the next theorem again, a of gamma be the smallest positive constant for which the inequality 4 holds, and gamma is natural number which is greater than or equal to 3, which satisfies this condition. M is positive function whose delta derivative is either positive or negative, and 19 holds. Then and phi is the largest root of this algebraic equation. Then again we have this vertical inequality. So again observe that we are replacing these auxiliary equations. The next theorem is that again a of gamma is the smallest positive constant, and gamma is natural number greater than or equal to 2, such that gamma plus 1 is greater than 20 times a of gamma. M is positive constant, a positive function whose delta derivative either positive or negative, and alpha is less than this, beta is less than this, and phi is the largest positive root of this algebraic equation. Then for any y satisfying this condition, again we have this Wirtinger-Type inequality. Again this one next. So just the same conditions, just we replace this algebraic equation, algebraic auxiliary equation. Phi is the largest positive root of this equation. Then again we have this Wirtinger inequality. Yeah, concluding remark is that so we have identified a suitable time scale for which the Wirtinger inequality, which is given in the paper 1 as the theorem 4.1 does not hold. We have given proper reason for the same why that theorem doesn't hold. Also, we have given certain examples of time scale for which this Wirtinger inequality holds, but it is not universally true for all time scale. Therefore, we formulated this version of Wirtinger inequality by appropriately redefining the auxiliary algebraic equation, which is equation number 4. And we have also identified certain time scale on which this theorem 4.1 is true. Further, using these existing inequalities, we have established some more new improved versions of Wirtinger inequalities on time scale. So this is concluding remark.